we're now going to take a look at an important class of functions known as the hyperbolic functions. Now these functions are important because they occur in many fields like differential equations and mathematical physics. They also share many properties that are similar to the trigonometric functions like identities and derivatives, but their graphs don't look anything like the trigonometric functions. In fact, they're not periodic at all. Now another interesting fact about these functions, as we'll eventually prove, is that one of them precisely models the shape of a hanging cable. And so that's a very interesting fact, but it'll take a little while for us to get to the proof of that fact. But it's really interesting. Now down here we have the definition for our hyperbolic functions, and you'll notice that we use a naming convention that is very similar to the trigonometric functions. And that's because they share many properties with the trigonometric functions, as we'll soon see. But keep in mind, they're not periodic, their graphs don't look anything like the trigonometric functions, they're not defined using right triangles at all. So we define what we call the hyperbolic sine function, or cinch. Notice we take the trigonometric function, the notation for the sine function, sin, and we just put an h on the end of it to indicate that we're dealing with the hyperbolic sine function. So this is denoted as cinch of x, and it's equal to e to the x minus e to the negative x divided by 2. So we define it using the exponential function e to the x. We define the hyperbolic cosine function, or Cosh. Notice we use the notation cos, and then we just add an h on the end of it. So we define the Cosh of x to be e to the x plus e to the negative x divided by 2. So all we did is change this minus right here to a plus. And we have our hyperbolic cosine function, or Cosh. And then we define the other hyperbolic functions in a manner that's similar to the way we define the trigonometric functions. So for example, the hyperbolic tangent, Tanh, is defined as cinch over Cosh. And when we take this quantity divided by this quantity, the 2's will cancel, and we end up with this. So here's the definition for our hyperbolic tangent: e to the x minus e to the negative x divided by e to the x plus e to the negative x. So that's the hyperbolic tangent. The hyperbolic cosecant is defined in a similar manner to the way the trigonometric cosecant is defined. It's 1 divided by the cinch. If we flip this, take 1 over this quantity, that will flip the fraction, and we end up with 2 divided by e to the x minus e to the negative x. The hyperbolic secant is 1 over Cosh, just like the trigonometric secant is 1 over cosine. So the hyperbolic secant, 1 over Cosh, and flipping this fraction here, we get 2 divided by e to the x plus e to the negative x. And then finally, the hyperbolic cotangent is 1 over the hyperbolic tangent, or flipping cinch over Cosh, the hyperbolic cotangent is Cosh divided by cinch. And if we take Cosh over cinch using these two rules right here, we end up with e to the x plus e to the negative x divided by e to the x minus e to the negative x. So these are all of our definitions here for the hyperbolic functions. Now let's take a look at what the graphs of these functions look like. So here we have the graph of all 6 of our base hyperbolic functions. Right here we have the graph of cinch. That's what it looks like. Now, to understand where this graph comes from, keep in mind that cinch is defined like this. So there I just split the fraction apart. Remember, we had defined it earlier as e to the x minus e to the negative x divided by 2. So I just split the fraction up like this, and notice we can write that as So what the cinch is, it's the sum of these two functions, e to the x over 2 and negative e to the negative x over 2. Now each of these functions are the graphs of these dotted curves over here. So the graph of this dashed curve is the function e to the x over 2, and the graph of this dashed curve is negative e to the negative x over 2. Now you notice as x goes to infinity, if we look at the limit of this, so just notice that as x goes to infinity, this piece of the function right here will be approaching 0. Because if I put a large number in here for x, like 1,000, e to the negative 1,000, that's like 1 over e to the 1,000. That's a very tiny number. So this piece is going to 0, so basically the cinch is behaving like this piece right here. So you notice in the graph over here, as x goes to infinity, the cinch is beginning to hug this dashed curve right here, which is the graph of e to the x divided by 2. On the other hand, as x goes to negative infinity, I put a negative infinity right there. Well, in that case, then, this piece of the function will be going to 0. This piece will be going to 0, because if I put negative 1,000 in here for x, now this will be a very small number, because it'll be like 1 over e to the 1,000 divided by 2. And now this piece right here, you see, this will be a positive value now, so this is not going to be going to 0. So you see, as we go to negative infinity, the graph of cinch becomes more and more like this function right here. So it begins to hug this dashed curve. And that's because this piece of the function goes to 0 as you move towards negative infinity. And we can analyze the other graphs in a very similar manner. For example, the Cosh. So here's our definition for the Cosh. Now you notice if we let x go to infinity, if we are moving in this direction, take a look at this graph over here. Notice we have two dashed curves here. The first one here is e to the negative x divided by 2, and this dashed curve is the graph of e to the x over 2. So in the limit as x goes to infinity, this piece right here will be going to 0. And so the graph of Cosh will essentially become this piece. So you see how the graph of the black curve, the Cosh, hugs that dotted line as we move towards positive infinity. Now as x approaches negative infinity, well, in that case, this piece right here is going to be going to 0. And the graph of Cosh will become more like the graph of e to the negative x over 2. And so we see as we move towards negative infinity how the graph of Cosh begins to hug this dotted curve right here, which is e to the negative x over 2. That's this one right here. And so you notice with Cosh, it never actually crosses the x-axis like cinch does. Notice cinch is 0 when x is 0, but if I put 0 in here for x, we get 1/2 plus 1/2, which is 1, so the graph of Cosh crosses the y-axis at 1. Now the graph of tangent we can analyze like this. Now you notice the graph of the hyperbolic tangent looks like this. And notice it has limiting values at 1 and -1 as you move towards positive infinity and negative infinity. And the reason that is because if we look at this definition back here for the hyperbolic tangent, notice that as x goes to infinity, this term, these two terms right here, both of these terms will be going to 0, and we'll be left with something that's basically behaving like e to the x divided by e to the x, which is approximately 1. And so that's why this limiting value is 1. On the other hand, as x approaches negative infinity, well, in that case, then, these two terms will be going to 0 as we go to negative infinity. And so the hyperbolic tangent will be basically behaving like negative e to the negative x divided by e to the negative x. Well, that's going to be approximately -1 then. And so we see as we move towards negative infinity how the hyperbolic tangent is flattening out at the line y equals -1. So it has a horizontal asymptote at y equals -1 and a horizontal asymptote at y equals +1. So that's the graph of your hyperbolic tangent right here. Now I'm just going to mention these quickly. We're not going to use them very often, but we have down here the graphs of our hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. Notice the hyperbolic cosecant has a vertical asymptote at x equaling 0, and that's because the sinh is 0 when x is 0. So the hyperbolic cosecant is 1 over sinh, and so when the denominator here is 0, you're going to have a vertical asymptote, and that occurs when x is 0 up here. So we see why we have that vertical asymptote. Also notice that as x goes to positive and negative infinity, the hyperbolic cosecant is approaching 0, and that's because the hyperbolic sine is going to positive and negative infinity. So 1 divided by a very large number is basically going to be 0. So that's why it approaches 0. Hyperbolic secant is 1 over Cosh. So notice we do not have any vertical asymptotes here for this graph because the graph of Cosh never crosses the x-axis. So Cosh is never equal to 0 anywhere. And over here we have the graph of the hyperbolic cotangent, which is 1 over the hyperbolic tangent. Notice it has a vertical asymptote when x is equal to 0 because the tangent function up here is equal to 0 when x is 0. So when x equals 0, you're going to end up with something like 1 over 0. That's a vertical asymptote. Notice also as x approaches infinity, the hyperbolic cotangent is approaching 1, and that's because the hyperbolic tangent approaches 1 as well. As x goes to infinity, so 1 over 1 is going to give you 1 back. And as x approaches negative infinity, the hyperbolic cotangent is approaching -1. And that's because the hyperbolic tangent is approaching -1 as well as x approaches negative infinity. And so 1 over -1 is going to give you back -1. So those are some important characteristics of the hyperbolic cotangent. And so that's a quick summary of the graphs of all of our hyperbolic functions. And before we leave these graphics, just take note, which one do you think looks like a hanging cable that we had referred to earlier? Well, it's this one right here, the hyperbolic cosine function. That actually models the shape of a hanging cable. And like I mentioned earlier, we'll take a look at that proof later on in the course. Now here we have listed some hyperbolic identities. Now you notice that these look a lot like trigonometric identities, but many of them differ by a sign somewhere. For example, let's take a look at number 1 here. So you notice we have Cosh squared x minus Cinch squared of x equals 1. Now compare that to cosine squared x plus sine squared x equals 1. So you see it differs by a sign here. Instead of a plus, we have a minus. And many of them are the same way. Some match up with trig identities, but others do not. So you have to be careful. Now you're not going to be required to memorize all of these, of course. You just have to be aware that they are available to you to use when working through some problems. Let's take a look at a proof of a few of these. Let's start with number 1. So we want to prove that this quantity is equal to 1. So what we'll do is we'll go back to our base definition for Cosh and Cinch involving the exponential function and algebraically manipulate it and show that we get 1 back. So let's write the Cosh squared and Cinch squared like this. So all we did is put in our exponential definitions for the Cosh and Cinch, and now let's algebraically manipulate this, the right hand side here, and show that we get back 1. Now when we square e to the x plus e to the negative x, when we FOIL this out, what we get is this. So that's what we get when we FOIL out e to the x plus e to the negative x. For example, I'll just quickly do that down here. So when we FOIL this out, e to the x times e to the x, that gives us e to the 2x. E to the x times e to the negative x, well, that's going to be e to the x times e to the negative x. We add the exponents together, and that's going to be e to the 0, and so we get back 1. And then when we go this term, e to the negative x times e to the x, we get back 1 again, and e to the negative x times e to the negative x, that's going to give us e to the negative 2x. So that gives us back this term. So the 2 is coming from this term, e to the x times e to the negative x. That gives us back 1. And then we have another one, e to the negative x times e to the x here, and that gives us back 1 as well. 1 plus 1 gives us 2 back. So that's how we get this term in the numerator right here. Now when we tackle the Cinch square term, we FOIL out the term right here again, just like we did over here, but we have a minus here. So what we're going to get is this. So notice we just get a minus there because of this minus right here. And then divided by 4, 2 squared is 4. And now we see that what happens here is we see we have a lot of cancellation. We have e to the 2x over 4 minus e to the 2x over 4, so these terms will cancel. We have e to the negative 2x over 4 minus e to the negative 2x over 4, so these will cancel because of this minus. And then we have 2 over 4 minus negative 2 over 4, so that's going to give us, right, because minus a negative is going to give us a positive, and we get back 1, and that's exactly what we wanted to prove. So we started with Cosh squared minus Cinch squared, went back to the base definition, and through some algebra showed that we got back 1, which is exactly what we wanted. Now the rest of these identities you can prove exactly in the same manner. You can go back to your base definition for your hyperbolic function and do some algebraic manipulation like we did here. Or sometimes you can also use previous identities that you've already proven. For example, number 3 right here, we could prove that one from number 1 without having to go back to the base exponential definitions. For example, if we started out with this identity now, and now what we'll do is we'll divide both sides by the Cosh. Okay, so just divide both sides. And now if we just divide both sides by Cosh squared, you'll see that we get number 3. And so what we end up with here is breaking this fraction apart. We get Cosh squared over Cosh squared. That's going to be 1. Cinch squared over Cosh squared. That's going to be the hyperbolic tangent squared. And over here, 1 over Cosh squared is the hyperbolic secant. And then just moving the tangent over to the other side, we get which is exactly what we wanted to prove. Now you could also go back to the base definitions. You could replace tangent with e to the x minus e to the negative x divided by e to the x plus e to the negative x and square that, and the same thing with the hyperbolic secant, and do some algebra and show that you get back 1. You could do it just like we did up here, but you can also do it this way, which is a little bit easier. And so all of these identities can be handled in a similar manner. Now let's take a look at some differentiation and integration rules of our hyperbolic functions. So here we have listed the derivatives of all of our hyperbolic functions. Now you notice that they look a lot like the differentiation rules for the trigonometric functions, but some of them differ by a sign. So for example, derivative of cinch is cosh, just like derivative of sine is cosine, but the derivative of cosh is cinch. Remember, the derivative of cosine is negative sine, so this one differs by a sign. Derivative of the hyperbolic tangent is hyperbolic secant squared x, so that's just like derivative of tangent is secant squared. Derivative of hyperbolic cosecant is negative hyperbolic cosecant times hyperbolic cotangent. That matches with the trigonometric derivative for the cosecant. Derivative of the hyperbolic secant is negative hyperbolic secant times hyperbolic tangent. So this one differs by a sign right there. Our trigonometric rule, remember, was derivative of secant is secant times tangent. So we had a plus there for the trigonometric version of this. And then the derivative of the hyperbolic cotangent is negative hyperbolic cosecant squared of x. So that matches with our trigonometric derivative. So the two that differ by a sign are this one right here and this one. All the other ones match with our trigonometric derivatives. Now let's take a look at a proof of one or two of these derivative formulas over here. Let's prove that the derivative of cinch is cosh. So we want to prove this. So we want to show that this is equal to cosh. Well, let's go back to our base definition for the cinch. And now just following rules for differentiating this is going to be just move the 1/2 out in front of the d dx. This piece right here is just going to be e to the x. And this piece right here, by the chain rule, that's going to be e to the negative x times negative 1, right? We have to let u be negative x. And we get this. So what we end up with then is so that's what we end up with. Of course, minus and negative becomes a positive, and we end up with, and that is the Cosh. Now all of the other ones can be proven similarly. Once you prove one or two of these, you can use those rules to prove the derivatives of the other ones. For example, derivative of tangent we could prove like this. Now remember, tangent is sinh over cosh. Now we just use the quotient rule here. Bottom times derivative of the top is going to be, now derivative of sinh is cosh, minus top times derivative of the bottom, that's going to give us, right, sinh times derivative of cosh is sinh, so I just wrote it as sinh squared, over the bottom squared, and we end up with, and remember from our hyperbolic identities, the numerator here, this is equal to 1, and so we end up with, and that's just the hyperbolic secant squared of x, because 1 over cosh is the hyperbolic secant. And there you go, we've just proven this one. So once you have these two proven, you can easily prove all of the other ones just by using quotient and product rules as needed. And then we have, because of these differentiation rules, we have our integration rules over here. So for example, the antiderivative of the hyperbolic cosine or cosh is sinh, because derivative of sinh gives you back cosh, right? Going this way, you take the derivative, it gives you back cosh. Antiderivative of sinh is cosh, because when you differentiate cosh, you get back sinh, because of this fact right here. Now remember, the integral for the sine function, that was negative cosine. So this one differs in sine from our rules for integrating the sine function. Antiderivative of hyperbolic secant squared is tangent, hyperbolic tangent, and so on. I'll let you read through these other rules down here. They come directly from these over here. So let's take a look at a few examples now. So let's just start by evaluating some derivatives. So let's evaluate the derivatives of these functions. So the first one we want to differentiate is the sinh of x squared plus 1. So we want to evaluate well, what we're going to have to do here is we're going to have to use the chain rule, you see, because the x squared plus 1 right here does not match up with what we're differentiating with respect to, so we have to use the chain rule. So we're going to have to let this term right here be a u. And so this is going to be d du of the sinh of u times, now the derivative of sinh is cosh, and so we end up with, now I'm going to put the u right back in place here. U is x squared plus 1. And du dx is going to be 2x. And I prefer to write that as, that way there's no confusion. The 2x is not being acted on by the cosh function. Only the x squared plus 1 is being acted on by the cosh function. Let's take a look at the second one here. So we want to differentiate this function. Well, we remember that the derivative of the ln of x is 1 over x. But in this case, you see the what's inside the parentheses here doesn't match with what we're differentiating with respect to. So we're going to have to use the chain rule again. So we'll let this be our u, and we simply write this as and this piece right here, of course, is 1 over u. And this is going to be, okay, what's the derivative of Cosh? Let's just write this out as. Now the u is Cosh of x, so let's write this as. And the derivative of Cosh is, using this rule right up here, the sinh. And so, interestingly here, we end up with sinh over Cosh. Well, that is the hyperbolic tangent. Now, so we've learned that the derivative of the natural log of the hyperbolic cosine, or Cosh of x, is the hyperbolic tangent of x. So that actually gives us an anti-differentiation rule. So we could say that the antiderivative of the hyperbolic tangent is exactly that right there. So we could say that. So that's actually a rule that we have. Let's take a look at this one. Let's find all the relative extrema for this function. X minus 1 times Cosh minus the sinh of x. So we want to find where this function has all relative extrema. So to find relative extrema, remember what we need to do is we need to take the first derivative and set it equal to 0, or find where it's equal to 0 or it does not exist. So taking the first derivative here, this piece right here, the first term right here, we're going to have to use the product rule. So x minus 1 times derivative of Cosh. Derivative of Cosh is sinh. Then Cosh times the derivative of x minus 1. That's just going to be 1, so plus Cosh times 1. And then minus the derivative of sinh is Cosh up here. And so we see these Coshes right here cancel, and we end up with our derivative being Now recall that to find where we have relative extrema, we want to find where this is equal to 0 or does not exist. And that happens, let's see, this term will be 0 when x is 1. So we know that x equals 1 is a solution to where the derivative is equal to 0. And the sinh of x, remember, that's 0 when x is equal to 0. Alright, so here are our two critical numbers. Now let's do a sine pattern technique. So we're going to look at the sine of our first derivative. So we mark off 0 and 1, and we pick some test values in between these. And we plug these numbers into the first derivative to see if we get back positive or negative values. So let's start out here with negative 1. If I put negative 1 into the derivative, so I get negative 1 minus 1, that's going to be negative 2. Let me write it out down here. So f prime of negative 1. Alright. Now, okay, so this is negative, obviously. Now, what's the sinh of negative 1? Well, if you remember what the graph of the sinh looks like. Graph of sinh goes like this. Right? So you see over here, the sinh is, like right here is negative 1. So the sinh of negative 1 is going to be a negative number. So this is going to be negative, negative. This is going to be positive. So positive here. Now let's plug another test value in, like let's say 1/2. Now if we look at f prime of 1/2, if we put that into our derivative, so this will be a negative number, 1/2 minus 1, so that'll be negative. And the sinh of 1/2, that is positive. See from the graph over here, like right here is 1/2, say, we see that the sinh is positive. So this quantity is going to be negative. And then let's pick another test value like 1. When we put that, oops, sorry, not 1. Let's pick another test value like 2. So plugging 2 into our derivative here, we get 2 minus 1 is 1 times the sinh of 2. Well, this is obviously positive. This quantity here is positive. We can see that from the graph of sinh over here. And so this is going to be positive, and so we get positive in this region. So this is where our function is increasing from negative infinity to 0. Then it's decreasing from 0 to 1. Then we're increasing from 1 to infinity. And so therefore, we see that 0, we're increasing and then decreasing. This is where we're going to have a relative max. And at 1, we are decreasing and then increasing. So we're going to have a relative minimum. And so therefore, let's state that down here. So therefore, we have a relative min occurring when x equals 1, or the point on the graph where your relative minimum would be, and if I put 1 into my original function right here, I would get, this is going to be 0 here because I get 1 minus 1. I'm going to get negative the sinh of 1. So that's the point on the graph where you have a relative minimum, and then you have a relative maximum occurring when x equals 0, or this is the point on the graph if I put 0 in here for x over here. 0 in here for x, I'll get negative 1 times the cosh of 0 minus the sinh of 0. The sinh of 0 is 0. Right, here's the graph. It crosses the through the origin right there when x is 0. The cosh of 0 is 1, remember. So we're going to get here negative 1. And there are the relative extrema for this function right here. Let's just take a quick look at the graph of this function and verify what we just found right here. Verify that these values represent relative extrema. And here we have the graph of the function that we just found the relative extrema for right here. That's the graph of y equals x minus 1 times the cosh of x minus the sinh of x. And we see from the graph right here we do have relative extrema. That point right there is 0, negative 1. That's the one that we found. And right here is 1, negative the sinh of 1. Once again, notice if I put 1 up in here for x, we get this term being 0, and I recover negative the sinh of 1. So that's where this is coming from. And yes, it does look like we have relative extrema at the points that we identified. And finally, let's take a look at this example. Let's evaluate the following indefinite integrals. So we want to start with the antiderivative of the cosh of 2x dx. Let's do this one first. Well, looking at our rules over here, we see the antiderivative of cosh is sinh, but we have a 2x right here. So this looks like an easy substitution. We would just let u be 2x. in which case, and then doing our substitutions, 2x becomes u. dx is going to become du over 2 when I divide the 2 underneath the du. Pull the 1/2 out and in front. And now the antiderivative, this right here, looks just like what we have right here. So this piece is going to be the sinh of u. And then substituting back in 2x in for the u, we get our answer. And there we go. Let's take a look at this one. So here we want to evaluate the antiderivative of this function. Now this one's a little bit trickier. Let's think about some type of substitution we could do. Let's think if I let u be some piece here, perhaps I could let u be either Cosh or Cinch, and then I could recover the rest from the du part. Well, in this case, we're going to want to let u be the sinh of x. You see, because then du will be Cosh x dx. And so we see that this part right here, this will become u squared. And the Cosh x dx, the rest here, that part right there, will become du. And so doing all of these substitutions, then we get and then the antiderivative of u squared, of course, is u cubed over 3. And then substituting sinh in for the u, we finally get our answer. And there we go. That is our antiderivative for the Cosh of x times sinh squared of x. And you can verify that by differentiating this, you do indeed recover Cosh times the sinh squared. And we can just verify that here quickly. Notice that if we differentiate, this, we would have to use the chain rule. So we would have to differentiate with respect to the sinh of x first. So this would be and then multiply by du dx, which is like that. So that's what our derivative would turn out to be. Notice how I let u be sinh x here to apply the chain rule. And you see how these 3's cancel. And we get sinh. And the derivative of sinh, this is du dx right over here. That is just the Cosh. And we get exactly what we wanted. So that just verifies that the derivative of this right here does indeed give us back what we wanted, Cosh times sinh squared. And that concludes this video on an introduction to hyperbolic functions.